We have seen previously that the pressure in a fluid increases as a function of depth, as the fluid at greater depths has to support the weight of the fluid above. Now we want to show that it is also possible to increase the pressure in a fluid by applying a force to it. Consider an enclosed fluid, for example the air in an enclosed house, or the water in an enclosed pipe. We will assume that the fluid is static, which means it's not moving. If we neglect gravity, then the only forces that act on the fluid will be the normal forces from the container walls. Consider two different points in the fluid, P1 and P2. Since the fluid is static and we are neglecting gravity, the pressure at P1 and P2 must be equal. If it wasn't, then the fluid would flow from the higher pressure point to the lower one, which would violate the condition of the fluid being static. If we now apply a force to one of the container walls with a piston, for example, the increase in pressure in the fluid will be uniformly transmitted throughout the fluid and into the container walls. This is a statement of Pascal's principle. Consider the example of two interconnected cylindrical chambers of different diameters as shown in the figure. The two cylinders are completely filled with a fluid. We can cap the top of each chamber with a fitted piston that is free to move in response to changes in the fluid's pressure. If we know the pressure P1 directly beneath the bottom of the small piston, then the pressure deeper in that cylinder, say at point A, would be equal to P1 plus rho GH. The important point is that the pressure P1 adds to the pressure rho GH due to the depth of the liquid at any point, whether that point is in the smaller cylinder, the connecting tube, or the larger cylinder. Therefore, by Pascal's principle, if the applied pressure P1 by the small piston is either increased or decreased, that change in pressure will be uniformly transmitted throughout the fluid. The usefulness of this result is obvious when we calculate the force F2 produced at the large piston. As long as the tops of the left and right cylinders are the same level, the pressure increment rho GH will be equal to 0, and P1 will equal P2. Each one of these pressures can be written as a force per unit area. Solving for F2, we find it is directly proportional to F1 and to the ratio of the cross-sectional areas of the two cylinders, A2 over A1. The force F2 can be made considerably large if the ratio of the two areas is large. Such a device could be used, for example, as a hydraulic car lift. It might seem like we're getting something for nothing, as a very large output force is created by a much smaller input force. However, the work done by each piston must be the same. Therefore, the small input force will move its piston through a greater distance than the larger output force moves its piston. In the next section, we return to the concept of pressure as a function of depth, and we will see that this results in an upward force on an object that is completely or partially submerged in a fluid.